Now that you understand how to describe motion in many methods, you will change your focus to applying the concepts of the mathematical tool known as the vector to also assist you in making calculations related to kinematic quantities. Follow the arrow to continue along the path into the next part of the lesson on vectors. Other vector quantities that we have encountered so far are displacement and acceleration. Velocity is a vector because it has two pieces of information: how fast something is moving and in which direction it is moving. It is impossible to convey both pieces of information, magnitude and direction, with simply one number. For instance, if we said that a car's velocity was 70 miles per hour, that would tell us nothing about the direction. So we would have to instead say 70 miles per hour at 10 degrees north of east. Often it is inconvenient to draw pictures to represent something, so people still look for ways in which to describe it merely with numbers, even if they have to use more than one number. Another way to represent a vector is using an arrow. The arrow is a convenient symbol for a vector quantity because it allows us to convey both pieces of information in one shot. The length of the arrow is the magnitude of the vector, and the direction in which the arrow points is the direction of the vector. For instance, to describe the car we were just talking about earlier, 70 miles per hour at 10 degrees north of east, we would simply draw an arrow like this. This is an example of representing vectors with polar coordinate system notation. As a technician, you can easily draft these vector quantities into diagrams which will assist you in describing how to make calculations using vectors. In this example, the two numbers a sub x and a sub y are called the components of the vector a. Note, vectors are usually denoted with bold-faced letters or letters with arrows above them. So vector a equals a sub x, a sub y, or in this example, a equals 68.9 miles per hour, 12.2 miles per hour. This representation is called the rectangular or Cartesian representation. In case of representing a two-dimensional vector, there are also three and even four-dimensional ones, but fortunately we will not be using them in this class. We use two numbers that can be figured out from the image as shown. There is another way in which you can represent a vector using two numbers: polar representation. In a way, we have already been using this representation. Basically, the two numbers are the length or magnitude of the vector and the direction, the angle measured with respect to the positive x-axis in the counterclockwise direction. Again, it is useful to note that we are describing tools here, methods in which a student can apply the description tools of physics to kinematic equation-based problems. The polar representation will become most useful in the lesson on rotational motion. When adding and subtracting vectors, it is most convenient to do so in the Cartesian representation. So if you are given two or more vectors in the polar representation, first convert them to the Cartesian representation and then add or subtract them. Review this example. This is a review from earlier lessons. Can you remember the concepts? You can also add vectors pictorially, as shown. Take the second vector and slide it without changing its length or direction so that its tail coincides with the head of the first vector. Then draw a third vector starting from the tail of the first vector to the head of the second vector. This third vector is the sum. Note, the order of the two vectors can be interchanged, such as vector addition is commutative. Similarly, you can also subtract vectors pictorially as shown. Take the second vector and flip it around so that it has exactly the same length as before, but is just pointing in the opposite direction. Take the flipped second vector and slide it, without changing its length or direction, so that its tail coincides with the head of the first vector. Then draw a third vector starting from the tail of the first vector to the head of the flipped second vector. This third vector is the difference. Note the first and second vector cannot be interchanged, i.e. vector subtraction is not commutative. These drawings of vectors in a draftsman-like fashion are important steps in helping the technical student understand the mathematics of vectors. You should now have a basic understanding of how to represent motion via a number of methods. These multiple representations are the best way to help you learn to understand the application of motion in physics. Ask your instructor for any specific homework assignment beyond this point. In this lesson, you covered the following objectives.